Hey everybody, this is Mrs. Mancuso, and today's video is about linked genes. So here we have a fruit fly, and fruit flies are really cool to work with because they have a really short life cycle, so you can see multiple generations in a short amount of time. They're really easy to use, they're small, they're cheap, you can store a whole bunch in a small space. They only have 4 chromosomes, so there's a really great chance that you're going to be able to study linked genes. Here's some cool traits. So all of the normal traits, we call them wild. So having red eyes, that's wild type. Here's a mutant. To be a mutant is to have white eyes. And then, of course, these are both males, and you can tell because they have the really dark end to them. Okay, I just talked about wild type and I talked about mutant. Since there's only 4 chromosomes, good chance that we're going to be able to see linked genes. All right, so problems. So let's get started. So if we cross a hybrid, so if we cross a fruit fly that's heterozygous for normal, so wild body color and normal wing shape, so that also wings are wild, with a homozygous recessive, so having a black body and have vestigial wings. Vestigial wings is like if the fly had little wings like this, so they don't work very well. So here's our cross. So we want to come up with all of our possible gametes for this parent first. So it could be big B, big N, could be big B, little n, could be little b, big N. Whoops, sorry, not sure why I keep doing that. Could be little b, little n. All right, so we do the cross. And the only possible gametes for this parent are little b, little n. So we would end up with normal, normal, or wild type, wild type. We would end up with normal and vestigial wings. So normal body color, vestigial wings. This one we would end up with black body and normal wings. And here we'd end up with black body and vestigial. So this comes out 1 to 1 to 1 to 1. All right, so let's slide over here. We do not get that data. So we get these huge numbers that are just like the parents. These are the kids, but those phenotypes are just like the parents. And then over here, these two are really rare. They must be due to recombination of these linked genes. So right away, having this crazy numbers, these are nowhere near 1 to 1 to 1 to 1. So instead, the results mean that the body color and the wing shape genes are linked. And each time I say linked, I mean they are on the same chromosome. All right, so what leads to this genetic recombination, the production of offspring with new combinations of traits? So what led to these new combinations? So if the wild type and the normal stuck together, and the black body and the vestigial stuck together because they were on the same chromosome, how would we get these new combinations? And we get them from crossing over. So in a normal genetic recombination, like if I go back to this one, our normal recombination, the reason why we make a Punnett square and why we have all these possibilities is because of independent assortment. That means each of the chromosomes line up on their own during meiosis and they separate. And that's why we do a Punnett square. When we do this, we're literally showing the separation of the pairs of chromosomes and all the possibilities you could get. But in contrast, if you have linked genes and they're on the same chromosome, then they move together through meiosis. Oh, sorry, this one wasn't meiosis. I skipped what I read there. Genetic combination can result from independent assortment of genes based on different chromosomes. Okay, so one way to account for linked genes to express different phenotypes is through, okay, so we account for it through recombination. We see that they've recombined. And the percent of recombinant offspring, that's called our crossing over frequency. So how often do we get crossing over? Tells us how closely linked the genes are. It's related to the location of the genes on the chromosomes. So I'm going to put LMU. LMU stands for linkage map units. So basically, if this is my chromosome, I could have multiple genes on it. Gene A, gene B, gene C, and the crossing over frequency here to here, crossing over frequency might be 20% because they're pretty far apart. But the crossover frequency here might only be 5 because they're really close together. So the frequency of crossing over actually tells us how many linkage map units genes are apart from each other. All right, so to determine the percentage of crossing over between genes, not to determine, but by determining the percentage of crossing over, a linkage map is what we'll call it. So again, it's just like what I drew here. This would be a linkage map. The further the genes are on the map, the more crossing over will occur. So to calculate the crossing over frequency up here, I'm going to take these two. That's the part that's due to recombination. I'm going to add them together. So 206 plus 185 over the whole. So the whole is 965, 944 plus 206 plus 185. So I've pretty much got just the part that's the recombination overall. And I also want to do times 100. So I did not grab a calculator yet. Let me grab, here's my phone. All right, let's do this math here. So I'm going to do 965 plus 944 plus 206 plus 185. That gives me 2,300 on the bottom, and 206 plus 185, 391 on top. All right, I divide. I multiply by 100. 17%. So that tells me that these two genes, B and N, are 17 map units apart. So 17 would go right here. Okay, use these other genes with fixed recombinant frequencies to map the chromosomes. So I know that vestigial, that was my N, and now my I color, they are 8 apart. And black body, that was my B. So B and E are 9 apart. And then this was the one that I did. So B and N are 17 apart. So when I map the chromosomes, I am going to say, all right, across here, I'm going to take this 17 because that's really the furthest distance apart. So B and N are 17 apart. And I'm going to put my E here in the middle. And 8 and 9 equals 17. So the N to the E is my 8, and the B to the E is my 9. So there we go. The order of the genes would go B, then E, then N. All right, let's move on here and try some more. So American chestnut trees have multiple linked genes that are easy to notice and study. Hairy leaves are dominant over non-hairy leaves. So when you look at a leaf, ooh, such an artist. Sometimes you can actually see all these little hairs on the leaf, especially if you hold it in your hand and hold it sideways. So that's what a hairy leaf is. And then sterile male flowers are dominant over fertile male flowers. Cross a hybrid heterozygous. So we're always, when we're studying linked genes, we always cross a heterozygous with the dominant trait. So big A, big B, little b, with homozygous recessive. That's always our cross. Now, if I wrote this all out again, it would be this and this and this and this, and I would cross it with this, and I would get a 1 to 1 to 1 to 1 ratio. And so we scroll down here and we look at our data, and this is definitely not 1 to 1. So the ones that are the most common, see the hairy leaves and the sterile male flowers, those were both dominant, and non-hairy leaves and fertile male flowers are the 2 recessives. So these 2 in the middle are due to my recombination. So to figure it out, I'm going to put 148 plus 136 on top, and I'm going to add up 850 plus 148 plus 136 plus 860 on the bottom. So let me just grab my calculator here. 850 plus 148 plus 136 plus 860. I got 1,994, and then 148 plus 136, 284. So 284 divided by 1994 is equal to 14.2%. All right, let's scroll down here. So they're going to give us some more. So now we just did the distance between A and B. So A and B are 14 apart, we'll say. All right, now we're doing E. Show the cross that needs to be done to determine the crossing over between blooming and hairiness. So the hairiness gene was the A's. So I now need to cross E, E, A, A with E, E, A, A. I would expect 1 to 1 to 1 to 1. And here's my data. So that's a parent. This is a really low number, and this is the really low number. So those are my recombinants, and that one's like the parents. Crossover frequency. All right, so this time I'm putting 150 plus 100, so that's 250. Oh, sorry, I don't know why it's shifting a little bit on me. Over 1120 plus 250 plus 1130. Okay, so 1120 plus 250 plus 1130 gives me 2,500. Sorry. First time using this pen. So that's just going to be 10%, right? So 10%. So that tells me that my E's and A's are 10 apart. All right, and then lastly, a cross needs to be done between the flower sterility and the blooming time. So the flower sterility was my B gene. So now I'm doing it between the B and the A, right? Nope, I already did B and A. B and E. Yep, B and E. All right. So the cross that needs to be done would be this. I would expect 1 to 1 to 1 to 1. Here's what I get. Look for the low numbers there and there. Those are my recombinants. So I put 190 plus 210 over the whole thing. 600 plus 190 plus 210 plus 602. I add them all up. 600 plus 190 plus 210 plus 602. That gives me 1602 on bottom, and 190 plus 210, 400 on top. That's going to be like 25%. So 400 divided by 1602, yeah, 24.968. So I'm going to say that's 25%. So that tells me that my B's and E's are 25 apart. So I write down here what I got. So B and E, I got 25 apart. This one I got 14, and this one I got 10. So again, I go for this one that's the furthest apart. B and E are 25 apart. And so A is going to be a little bit closer to E. So the distance here is 10, and the distance here is 14. And 10 and 14 is about 25. It's a little bit short of it, but that is what makes the most sense with what I have been given. So it's pretty cool. I could take these 3 different genes, cross them each with each other until I've done each combination, figure out their frequencies, and then map it. So here's some more practice. So what I want you to do is draw out your line and figure out, like, okay, if Q and S are 17 apart, where else could the rest of these be? So if Q and R are really far apart here, or P and S, if the P works out here, it's like doing a little puzzle. So the P and the S, if this is 12, 12 and 5 gives me 17. Q and P is 5. Okay, so I used this one. P and S. I used this one. And I used this one. So now I got to figure out where the R is. So P and R is 8. So, and Q and R is 13. So it would have to be here. So this would be my R. So Q and R, this would be 13. And then this would be 8. And that works out because 5 and 8 equals 13. All right, so that's how you do it. So go ahead and do the next one on your own and then let me know if you have questions.